So we are ready for emerging challenges and future concepts. And our first speaker will be Andy Lawrence. So we have a very packed session. So I'll try to get things moving very fast. Yeah. Thank you very much, Andy.
Okay. Latecomers don't get the donuts. That's the rule. Good afternoon, everybody. And hopefully in a few minutes, I'll clarify my rather strange title. Okay. About 18 months ago, a bunch of us, many of whom are in this room, wrote this article, Making the Broad Case for Space Environmentalism, including the use of astronomical use of the dark sky as use of that environment. So I still believe this is the right approach, but I wanted to examine critically whether it made sense, as some people are doing, to adopt other general environmental and ecological concepts, whether it made any sense, whether it's useful. The bottom line is, roughly speaking, no, but let's just see. All right, so there's a lot of vagueness in this area. Is orbital space an ecosystem? No, it doesn't have the kind of feedback loops and resilience features that ecosystems are supposed to have. I hope Fiona Thompson is listening online, because she's made this point multiple times. The human economic system that uses orbital space is a kind of human ecosystem, but I don't think that really helps us much. Carrying capacity. I've grown to hate this word. It's used inconsistently in different fields. And it's well defined in ecology, at least, but there, basically, it means an equilibrium level. If you overshoot or undershoot, you return to the carrying capacity level, which is not what we're looking for. Tipping point, incredibly vague every time people use this. Normally, going right back to the limits to growth, 1972 and all that, you get a turnover if there's some kind of finite resource, non-renewable resource that's becoming depleted. It's not obvious that applies here. However, having said that, here's this debris model for one of the JSON models that we adapted for that Nature paper. I haven't got time to go into details, but the accumulating collisions could cause a turning over of the net number of active satellites with time. It's very model dependent. It's in one shell, but here's the key point. It happens after decades. So I'd rather like something to be important a bit sooner than that. So I'm not sure we want to hitch our wagon to that. Maybe better, I've become very interested in the planetary boundaries framework. The latest version of the Stockholm School of Planetary Boundaries just came out. Their method is to define metrics of various kinds, such as the amount of CO in the atmosphere, the degree of ocean acidification, and so on, and to claim that we're going beyond safe boundaries in now 6 out of 9. And they always leave this space for novel entities. So perhaps we could try and think of a metric to put in there and get adopted into this kind of framework. Maybe collision risk, some metric that quantifies optical interference, etc. But a variant of this you probably have heard of, developed and touted by Kate Rayworth in 2017, is donut economics. So in the Rayworth version, not only is there an outer boundary, there's an inner boundary. We do want economic activity for health, for fairness, for justice, and so on. So you want to be in between the inner boundary and the outer boundary, and that's the nice place for humanity to be. So that's the donut. Why is this considered a work of economics? The other big point that Rayworth makes in this book is that staying within that donut is incompatible with the standard economic mantra of endless growth. Okay, so we all know, as physicists, as most of us are, or engineers, that a fixed percentage rate of growth leads to an exponential. So I asked myself, are we in fact looking at an exponential? And I thought, I don't have seen anybody do this, but I plotted the famous growth curve in log linear coordinates. It's very illuminating. So you can see 3 distinct epochs, each of which are exponential, but with a different doubling time. There's the original space age with a doubling time of about 1.2 years. several decades of traditional space with a doubling time of about 17 years. And now this is new space with a doubling time of 1.7 years. Now I plotted that with and without Starlink, not to be mean to Starlink as usual, but to emphasize that it was starting before Starlink. New space was a thing. It's not just Starlink. It's the worst, but it's not just Starlink. Now, at this point, you may be thinking, okay, what about the junk? So here we go. So this is the junk in the sense of tracked debris plus parts plus rocket bodies, etc. And you can see that at first that leapt up faster than the number of active satellites. Then it kind of settled into kind of being roughly similar. But now it seems to be not responding to the new space age. So I thought, well, we can do better than this. What I did was to divide the junk by 13. That's what we have here. It's very impressive. You can see for a long period, every active mission created 13 pieces of junk. That's what happened until you get to this dotted line. Oops, there. So that's 1995. So what happened there? That's when the NASA Orbital Debris Office first set out its debris mitigation deadlines. Of course, a few years after that, it was improved, adapted, adopted by the IADC. So my first conclusion from this is that debris mitigation works, right, to first order. Oh, no, here we go. But you can also see that when there is growth, it's in the jumps, it's the collisions. And the two big ones we know about, Iridium Cosmos and the Chinese satellite, anti-satellite test. But also it's because we're increasingly using low Earth orbit and things do, by design or otherwise, re-enter. So here, that's the Russian ASAT test. It looks like a tiny blip in this logarithmic scale, okay? But most of it's gone back. Okay. Now, but other lessons to learn from this, I think, firstly, the reminder that it is the collisions that matter. And also the fact this tells us that stuff is coming down, okay? And it doesn't all burn up completely. So a big increasing issue is going to be liability. We have to have some kind of agreed collision risk metric, I think, and increasingly we're going to want something like third-party liability. And this is basically an international state-to-state thing. But in the UK, for instance, now there's a requirement for operations to have third-party insurance, which I think is not the case in most other places. Right, just a little bit more. Another way to look at this is to calculate the average number of satellites above the horizon. Now, this is not a proper model, okay, like you saw from Federico De Bruno or David Galadi. If you want to know exactly how many there are from your location, a given time of night, how bright they are, etc., you need a proper model. This is just a metric. An average number uses a very simple kind of 4-shell radial height model. But you can see the number of objects above the horizon growing. My favorite way of looking at this, and just to make, here's the key point first of all. Okay, thank you. These are our allies. This is a problem, obviously, for astronomy, and just thinking about the number, just forget about reflection and, or unintended, whatever it is, UEMR. Yeah, okay. It's all going to go with the number of these things that there are. The people who should also care about this, some of whom certainly do, are the space operators, okay? Because you have to see through the low Earth orbit constellations to reach GEO or to reach elsewhere in slightly different shell in LEO, etc. So as the population increases, line of sight collisions get more and more frequent, and the aggregate power contamination from all the side lobes and so on gets worse and worse. So life becomes harder for GEO satellites. It's not a coincidence that Viasat are fighting SpaceX, okay? This is basically why. This is what's going on, okay? And I think what we should align ourselves with. Very much ITU business, of course. So another way to look at this, second to last slide, is about in a similar simplified way, you can calculate the typical inter-satellite distance. So this is the lesson. We're inexorably heading towards a degree level separation, okay? So, and the thing about doing this log linear, look at exponentials thing, is forget all that geopolitical guessing about whose filings are going to work and so on. Just look at this as a system and extrapolate, because they are exponentials. Okay, so here's my big bottom line, right? I think the problem is the numbers, not the brightness. Can we please focus on the main issue? Brightness matters. It's really about the numbers. We should be asking people, not how many can I get away with? How many is enough? All right. I don't know how to do that, but I just feel strongly that is actually the problem. And then the sub-conclusions, be cautious with ecological concepts. People talk a lot of BS. New space is doubling every 2 years. Debris mitigation works, but we probably need a new collision liability framework. Operators have the same interference problem that we do. So we should align with them, I think. And we are heading towards degree scale separation. That's it. Thank you.
Unfortunately, we don't have so much time for question now, but there will be all the coffee breaks, and maybe we will have the possibility of talking on Slack.